Hi everyone, this is Dr. Jamarendra. Today let us have a look at one-dimensional steady-state heat conduction in plane walls. Mathematically speaking, Q would be a function of x alone when you talk about Cartesian coordinate system. If you look at radial systems like cylinders and spheres, Q will be a function of r alone. And for a system to be one-dimensional, one of its dimensions should be very small compared with the remaining. And majority of systems fulfill these requirements like furnace walls, steam pipes, boiler domes, etc. If you look at a furnace wall, the thickness of the wall is going to be so small compared with the lateral dimensions of the wall. Therefore, a furnace wall can be taken as a one-dimensional system. And for a system to be in steady-state condition, it must be in the given environment for longer periods of time, maybe an hour or even more. And if you consider plane walls, when I say a plane wall, I mean a wall made up of a single material, maybe aluminium, maybe cast iron, maybe mild steel, whatever it is. And if you consider a plane wall over here of some area A, thickness L, made up of a material having thermal conductivity K, then we have left side surface temperature T1, right side surface temperature T2. And we have T1 more than T2 such that there would be some heat transfer along x direction. Now we would be interested in finding out the expression for heat transfer rate and temperature profile in terms of available data. When I say available data, we have area, we have material, we have thickness, and we have both the surface temperatures. And this can be done by two methods. One is the classical Fourier law can be adopted. Other one can use the governing differential equation GD. And when you use Fourier law in a simplified form, it looks like Q is equal to minus Ka dt by dx. And you may recollect that in general, the Fourier law is given by Q is equal to minus Ka del t by del x. When you use this partial derivative, it implies that we are allowing temperature to vary with respect to x, y, and other coordinates. But when I say temperature is a function of x alone, this partial derivative will become ordinary differential. Therefore, our mathematics becomes simple. And we can simplify this equation by variable separable method, and we can find the heat transfer rate as Q is equal to Ka by L T1 minus T2. And we may note that when T1 is more than T2, we are going to have heat transfer positive, that's along x direction as it is proposed. By chance T1 is less than T2, Q will be negative, it will be going in the opposite direction. If T1 is equal to T2, there won't be any heat transfer. And by following a simple method, we can get to know that the temperature profile in the plane wall is given by T1 minus T by T1 minus T2 is equal to x by L. Therefore, this temperature profile is going to be linear, that is straight line, implying that the slope of the temperature profile remains same, doesn't matter whether we are at the left side or right side or somewhere in the middle. By chance we have unit area, then we can always calculate the heat flux, conduction heat flux, that's heat transfer rate per unit area as K by L times T1 minus T2 if area is not available. And similarly, one can adopt the governing differential equation, which can be given by d square t by dx square is equal to 0. And when you integrate this equation once, we get the slope of the profile. And when we integrate it again, we are going to get the general temperature distribution in terms of two constants C1 and C2, which can be evaluated using the given conditions that at x is equal to 0, on the left side we have t is equal to t1, at x is equal to L, that is on the right side we have t is equal to t2. And one can always get the same temperature distribution and heat transfer rate using these equations. And if at all area is not given, as I was telling, we can find the flux, which is K by L delta T, where we float another parameter delta T, which is T1 minus T2, known as thermal potential, which means the potential which is responsible for the heat conduction. Then many a times we feel that electrical analogy can be conveniently used to solve some powerful conduction problems or complex conduction problems. And before we adopt the electrical analogy, let us have a comparison or analogical parameters. By way of a table, and current and heat transfer rate are analogous to each other. Thermal potential is analogous to voltage potential, and thermal resistance is analogous to the electrical resistance. And if you consider a classical resistance, electrical resistance, we have some current I flowing across some voltage V, then there is some resistance R, then as per the famous Ohm's law, I is voltage by resistance. And we can have the similar circuit diagram, analogical thermal circuit, wherein V is replaced by delta T and R is replaced by RTH and I is replaced by Q. Then Q is given by delta T by RTH. And if at all you have unit area, then we can find Q prime as delta T by ARTH, where ARTH represents the unit thermal resistance in meter square degree centigrade per watt. And by just comparison, we can realize that thermal resistance is L by Ka and unit thermal resistance is L by K. And we can see that for the given geometrical parameters L and A, our thermal would be 0 if K is infinity. That material we call it a perfect conductor. And our thermal will be infinity if K is 0, which we call it a perfect insulator. And just this equation can be appropriately analyzed when you have same heat transfer rate, same area, same wall thickness. Then the product of thermal conductivity and thermal potential is a constant. When K is infinity, delta is 0, which means that the profile will be horizontal. And when K is 0, delta T will be infinity, the profile will be vertical. And these two materials are known as a perfect conductor and perfect insulator, respectively. And for all ordinary materials, temperature profiles are given by these blue colored lines 1, 2, 3. And you can see 1 requires minimum potential, it must be the best conductor, whereas 3 requires maximum potential, it must be the poor conductor, sandwiched by 2. Therefore, for these three materials, we can say that K1 is more than K2 is more than K3. 1 may be copper, 2 may be aluminum, 3 may be cast iron. So we can always know that better the conductor, lesser is the slope or lesser is the potential required. And we can always carry out similar analysis using governing differential equations. And this governing differential equation can be derived from the basics, from the fundamentals, particularly those who are looking for engineering services. This could be a simple derivation, and we consider an elemental strip in a plane wall of thickness dx, and some heat is peeping in at a rate of del qx and some heat is coming out at a rate of del qx plus dx. And for this elemental strip to be in steady state condition, heat coming in should be same as heat going out. So delta qx should be equal to delta qx plus dx. Then we can write delta qx as minus ka dt by dx using the Fourier law. And using Taylor series, this can be extended as delta qx plus dx as delta qx plus d by dx delta qx dx. And when we incorporate these two laws in this energy balance equation, we are going to get the governing differential equation, which can be integrated 2 times to get the required temperature profile and the heat transfer rate subject to the appropriate boundary conditions. We can as well get the general heat governing differential equation by simplifying general heat conduction equation in the Cartesian coordinate system or XYZ system. By following a standard procedure, we can show that the general heat conduction equation is given by del square t by del x square plus del square t by del y square plus del square t by del z square plus q dot by k is equal to 1 by alpha del t by del tau for an isotropic material, which means that constant properties. Here first term accounts for conduction along x direction, second term takes care of y conduction, third term accounts for conduction along z direction, fourth term accounts for internal heat generation, and right hand side we have unsteady term. Here this q dot represents rate of internal heat generation per unit volume, which means that you may have some heat sources inside the system like a furnace or an electric coil, due to which heat could be generated at a rate of some q dot watts per meter cube. And alpha is a material property known as thermal diffusivity, having the units meter square per second. And this equation 1 is so complex that our available mathematics cannot be used to solve this. Therefore, we need to simplify this equation by incorporating suitable assumptions. One can begin with no heat generation. Then fourth term vanishes. We are going to get equation 1a, no heat generation. Next, we can say that steady state heat transfer. Temperature is independent of time, so RHS becomes 0. We get equation 1b. One can have a blend of both. We can say that no heat generation, steady state heat transfer. We are going to have x conduction plus y conduction plus z conduction is equal to 0. This is known as the famous Laplace equation. Like this, we can have so many simplifications to have this equation 1 in a more compatible form. And the simplest one is that temperature is a function of x alone, which means that one-dimensional steady state, no heat generation. This implies that temperature does not vary with y, with z, with time, and you don't have anything inside the wall. As a result, first term becomes 0. Since temperature is a function of x alone, del can be replaced by d. So d square t by dx square is equal to 0. We have come back to GDE again. So this is the governing differential equation for the temperature distribution in a plane wall subject to 1D steady state conditions. Now these are all certain simple procedures by way of which one can handle plane walls. Now let us have a look at some general problems which could be useful to write any of the examinations. First problem, an aluminum wall of 20 centimeters thickness and 0.3 meter square area has its left and right side surfaces maintained at 90 and 25 degrees centigrade respectively. And from data books for aluminum, K can be taken as 198, and I would like to determine heat transfer rate in kilowatts, thermal resistance in Kelvin per watt, temperature at some location 14 centimeters from the left side surface, and the distance from the origin where the temperature would be 35 degrees centigrade. So here first and foremost thing is that we must have the data in compatible term or in consistent dimensions. The thickness is 20 centimeters. All linear dimensions must be in meters. It's going to be 0.2 meters. Area 0.3 meters square. T1 90, T2 25, delta T is 65 degrees centigrade, K is 198. Just now we have seen that Q is Ka by L delta T, and if we incorporate all this data, Q is going to be 19,305 watts. Since we want to have it in kilowatts, divide by 1000 to have it as 19.305 kilowatts. Then as per electrical analogy, we can write Q as delta T by RTH, and Q is available, delta T is available, so RTH is delta T by Q, which is going to be 3.367 10 power minus 3 degrees centigrade per watt. Because delta T is 65, Q is 19,305, and electrical analogy is shown over here. And sometime back we have seen the temperature profile as T1 minus T by T1 minus T2 is equal to X by L. T1 and T2 are available, L is available. When X is given, you have to get T. When T is given, you have to get X. Now X is given as 14 centimeters, 0.14 meters. Then if we substitute this data over here, then we get temperature at x is equal to 14 centimeters as 44.5 degrees centigrade. And you like to know the position where temperature is 35 degrees centigrade. So here 90 minus 35 by 65 is equal to x by 0.2. X comes out to be 0.1692 meters, and if you multiply by 100, 16.92 centimeters. So at x is equal to 16.92 centimeters, you are going to get this temperature of 35 degrees centigrade. So this is a general problem involving all the calculations. And if we do some problems involving only one step, a plane wall of 18 centimeters thickness conducts 110 kilowatt per meter square of heat across a potential of 52 degrees centigrade. Find the thermal conductivity of the material. Also identify the material from the following. So based on the value of K, you have to identify whether it is wood, aluminium, copper, or mild steel. So if you jot down the data, thickness is 0.18 meters, and based on the units kilowatts per meter square, it has got to be heat flux. Whenever the units are kilowatts, it's heat transfer rate. Kilowatt per meter square, it is going to be heat flux. So Q prime is equal to Q by A is 110 kilowatt per meter square, and always it should be in watts per meter square. So multiply by 1000, it's going to be 1,10,000 watts per meter square. Delta T is 52. This is 52 degrees centigrade as per the given data. Therefore, if you substitute this, you are going to have Q prime is equal to K by L delta T, or K is equal to Q prime into L divided by delta T, which is going to be 380.76. Around 380, the material has got to be copper. So option C should be correct. Then lastly, a cast iron wall offers a thermal resistance of 0.2 Kelvin per kilowatt when the area of the wall is 9 meters square. Find the wall thickness in centimeters. For cast iron, take as 54 watts per meter Kelvin. Again, thermal resistance is 0.2 Kelvin per kilowatt. That's 0.2 10 power minus 3 Kelvin per watt. Area 9 meters square, K is 54. And we know that R thermal is L by Ka. So L will be R thermal into Ka. And if you substitute all this, your L will be 0.0972 meters. And if you multiply by 100, it's going to be 9.72 centimeters. So there are some very simple problems, ordinary problems, which may be useful to score a mark or a couple of marks. With this, we have completed plane walls, and next session we will have a look at one-dimensional steady-state heat conduction in hollow cylinders, followed by hollow spheres.